Something is wrong with the stars closest to Earth. Not catastrophically wrong, not obviously wrong, but persistently, measurably wrong in ways that do not resolve when instruments improve or models update. Proxima Centauri produces flares that exceed what its rotation rate should permit. Alpha Centauri refuses to reveal planets that detection methods insist should be visible. Barnard star generates signals that appear in datasets and then vanish upon reanalysis. Wolf 359 flares at frequencies that place it outside normal population statistics. These are not dramatic failures of physics. They are small, precise deviations, the kind that might be dismissed individually, but accumulate into a pattern when examined across the entire nearby stellar sample. The pattern suggests either that our models of stellar behavior contain systematic errors, or that the stars within a few parsecs of Earth are genuinely different from stars elsewhere in the galaxy. Both possibilities carry significant implications for astrophysics, for the search for habitable worlds, and for our understanding of the local cosmic environment. The spacecraft sits in silence at the edge of the solar system, sensors calibrated, trajectory plotted. The mission is straightforward. Visit the nearest stellar systems in sequence, collect data at each stop, compare observations against predictions. The first target lies 4.24 light-years ahead, Proxima Centauri, the closest star to Earth beyond the Sun. The ship's drive engages without sound. The stars do not visibly shift. Only the instruments register the change in velocity, the beginning of the long crossing toward our nearest neighbor. We drop out of cruise velocity near Proxima Centauri. A dim red sphere occupies the forward display, barely brighter than the background star field. At 2,800 Kelvin, Proxima emits most of its radiation in infrared wavelengths invisible to human eyes. The visible glow is faint, ruddy, unremarkable. Sensors immediately begin recording across all frequencies. The core anomaly at Proxima involves its flare activity. This star erupts violently and frequently, releasing bursts of radiation that can increase its brightness by factors of several within minutes. In 2019, instruments recorded a superflare that released more energy in seconds than the Sun typically produces in an hour. For a star with only 12% of the Sun's mass, orbiting once every 83 days on its axis, this output contradicts basic predictions. Rotation drives magnetic activity in stars. Faster rotation produces stronger magnetic fields and more frequent flares. Proxima rotates slowly, yet it flares as intensely as stars spinning 10 times faster. The mismatch between rotation rate and activity level exceeds measurement uncertainty by a significant margin. Standard astrophysics explains this through the fully convective nature of red dwarfs. Unlike the Sun, which has distinct radiative and convective zones, Proxima's interior churns entirely from core to surface. This convection generates magnetic fields through mechanisms different from the solar dynamo, mechanisms that may not depend as strongly on rotation. The explanation is plausible and widely accepted, but a detail complicates this picture. Proxima is gravitationally bound to Alpha Centauri, orbiting the binary system at roughly 13,000 astronomical units. This orbital relationship has persisted for billions of years. One alternative hypothesis proposes that long-term gravitational interactions with Alpha Centauri may have altered Proxima's internal dynamics, its rotation history, or its magnetic field configuration in ways that standard isolated star models do not capture. If stellar activity can be influenced by distant companions over geological timescales. The relationship between rotation and activity may be more complex than current frameworks assume. The ship's sensors also detect Proxima Centauri b, the planet discovered in 2016, orbiting within the star's habitable zone. Each flare bathes this world in radiation that standard models suggest should strip its atmosphere over time. Yet the question of whether planets can retain atmospheres under such bombardment remains genuinely open, dependent on magnetic field strengths, atmospheric compositions, and replenishment rates that cannot be measured from this distance. The data download completes. The ship rotates slowly, reorienting toward the next target. Alpha Centauri lies just 0.113 light-years further from Earth than Proxima, but our trajectory takes us there in a matter of hours at cruise velocity. The instruments recalibrate as the new target comes into sensor range. Alpha Centauri resolves into two distinct sources as we approach. Alpha Centauri A, slightly larger and brighter than the Sun, dominates the display. Alpha Centauri b, slightly smaller and cooler, orbits its companion at distances ranging from 11 to 36 astronomical units, depending on orbital phase. The binary has been observed from Earth for centuries, its properties cataloged with precision rivaling any stellar system beyond the Sun. The core anomaly here involves planets, or rather their absence. Alpha Centauri has been a primary target for planet searches since the first exoplanet discoveries in the 1990s. The system's similarity to our own made it seem ideal for hosting Earth-like worlds. Decades of observation using multiple detection methods have produced results that are frustratingly inconclusive. In 2012, researchers announced Alpha Centauri BB, a planet orbiting Alpha Centauri b with a period of 3.2 days. The detection, based on radial velocity measurements showing stellar wobble, appeared robust. Subsequent reanalysis revealed that the signal might be an artifact of data processing, rather than a genuine planetary signature. The detection was retracted. Later studies have proposed additional candidates, including a possible planet around Alpha Centauri A, but none has achieved confirmation. The pattern is consistent. Signals appear at the edge of detectability, generate excitement, then dissolve upon closer examination. Standard interpretation attributes this to the difficulty of detecting small planets in a binary system. Both stars exhibit surface activity that introduces noise into spectroscopic measurements. The gravitational interaction between the stars creates complex dynamics requiring sophisticated modeling. Against this background, Earth-mass planets might produce signals too weak to extract reliably with current instruments. An alternative hypothesis questions whether the binary configuration itself suppressed planet formation. Dynamical simulations indicate that stable planetary orbits exist only within about 3 astronomical units of either star, or beyond 70 astronomical units from the system's center of mass. The close passages of the two stars during their 80-year orbit might have disrupted protoplanetary disks, truncated material available for planet formation, or destabilized early planetary embryos. If binary dynamics can inhibit planet formation, the apparent absence of detected planets might be genuine, rather than an artifact of detection limits. The sensors continue recording as we hold position between the two stars. Temperature readings, spectral analysis, magnetic field measurements all flow into storage. The binary rotates slowly in the forward display, the two stars tracing their endless gravitational dance. The ship's trajectory shifts again. The next target requires a longer transit. Barnard's star lies approximately 6 light-years from Earth, not much further than Alpha Centauri in absolute terms, but positioned in a different direction. The course adjustment takes several minutes. When it completes, new stars occupy the forward display, unfamiliar configurations marking our changed position in the local stellar neighborhood. We arrive at Barnard's star to find another red dwarf, slightly cooler than Proxima, notable for its extreme proper motion. This star moves across Earth's sky faster than any other, a consequence of its relative proximity combined with its actual velocity through the galaxy. From our position near the star, that motion is imperceptible. Barnard's star simply hangs in space, a dim red point indistinguishable from countless others, except for our precise knowledge of where we are. The core anomaly here involves a history of detections that proved false. In the 1960s and 1970s, astronomer Peter van de Kamp announced planets around Barnard's star based on astrometric measurements. By tracking the star's position over decades, he claimed to detect a wobble caused by orbiting companions. The claimed planets entered textbooks and popular accounts. Later analysis revealed that the wobble corresponded to modifications made to the observing telescope. When the optics were adjusted, the star's apparent position shifted in ways matching the instrumental changes rather than any real gravitational effect. The planets were not astronomical objects, but instrumental artifacts. The story did not end there. In 2018, a different research team announced a candidate planet, Barnard's Star B, based on radial velocity measurements accumulated over 20 years. This super-Earth, several times more massive than our planet, supposedly orbits in the cold outer reaches of the system. The detection remains tentative, classified as a candidate rather than a confirmed world, with the signal sitting at the threshold of reliable extraction. Standard interpretation treats these episodes as cautionary tales about the difficulty of detecting small signals and noisy data. Each claimed detection pushed the limits of available instruments, and each either failed confirmation or remains disputed. The pattern illustrates how science corrects errors over time while continuing to probe detection boundaries. An alternative hypothesis asks whether something about Barnard's star itself produces signals that mimic planetary signatures. Red dwarf surfaces feature complex activity, spots, plumes, convective cells that affect spectroscopic measurements. A large star spot rotating with the star can create apparent Doppler shifts resembling planetary wobbles. Stellar activity cycles operating over years or decades can introduce periodicities that overlap with planetary orbital periods. If Barnard's star exhibits activity patterns that systematically produce planet-like signals, the repeated pattern of tentative detections might reflect stellar properties rather than actual companions. The instruments record everything: spectral lines, brightness variations, magnetic field indicators. Whether these data will finally resolve the question of Barnard's star's planetary system remains unclear. The evidence accumulated over 6 decades points in contradictory directions. The ship moves on. The next stop is Wolf 359, a red dwarf 7.9 light-years from Earth. The transit is brief. When we arrive, another dim red star occupies the forward display, superficially similar to Proxima and Barnard's star, but with its own distinguishing characteristics. Wolf 3I59 is a flare star, like Proxima, prone to sudden increases in brightness from magnetic reconnection events. But here the anomaly is statistical rather than individual. Wolf 359 belongs to a population of nearby flare stars that appears to exceed predictions for a randomly selected stellar sample. Proxima Centauri, UV Ceti, Wolf 359, and several other red dwarfs within 20 light-years all display elevated flare activity. The concentration of active stars in the local neighborhood is higher than models predict for stars of these types drawn from the general galactic population. Standard interpretation attributes this to observational bias. Active stars are easier to study. They produce more detectable signals, attract more observing time, appear in more publications. The apparent excess of flare stars nearby might simply reflect the fact that astronomers preferentially observe interesting objects. An alternative hypothesis connects this excess to the local bubble, the cavity in the interstellar medium surrounding the Sun. This bubble, roughly 300 light-years across, was likely carved by supernovae over the past 10 to 20 million years. The interior contains hot, tenuous plasma, distinctly different from the denser interstellar medium elsewhere. Most analyses treat the local bubble as affecting only the space between stars. But if the bubble environment influences stellar magnetic activity through mechanisms not yet identified, stars embedded within it might systematically differ from stars elsewhere. The excess of flare stars nearby would then reflect environmental effects rather than observational selection. The sensors capture Wolf 359's current state, baseline luminosity, spectral characteristics, any flare activity occurring during our observation window. The star appears quiescent at the moment, but historical data indicates that eruptions can occur without warning. The pattern emerging from these first 4 stops is suggestive. Each star exhibits some anomaly, some feature not fully explained by standard models. The anomalies differ in detail, but share a common characteristic. They involve unexpected behavior that persists despite intensive observation. The ship continues its survey. The next several targets lie at increasing distances from Earth, each adding new data to the accumulating picture. Ross 128 appears in the forward display after a transit of several hours. This red dwarf, approximately 11 light-years from Earth, attracted attention in 2017 when radio telescopes detected unusual signals from its direction. The signals consisted of quasi-periodic broadband pulses that did not match known natural phenomena. Brief speculation about artificial origins circulated before further analysis attributed the signals to satellite interference contaminating the observations. The core anomaly here is not the radio signals themselves, which have a mundane explanation, but what the episode reveals about signal interpretation. Unusual observations are routinely explained through conventional mechanisms: interference, instrumental artifacts, previously unrecognized natural phenomena. This approach is scientifically appropriate, but it raises a question that is difficult to answer. If an unconventional signal existed, one requiring a genuinely new explanation, how would it be distinguished from noise? The templates used to classify signals are based on known phenomena. A signal outside those templates might be misclassified or dismissed rather than recognized. Ross 128 hosts a confirmed planet, discovered later in 2017, orbiting within the star's habitable zone. Unlike Proxima Centauri, Ross 128 is relatively quiet, displaying less flare activity than many red dwarfs of similar type. This quietness makes its habitable zone planet a more promising candidate for atmospheric retention. The contrast between Ross 128 and Proxima illustrates the diversity among nearby red dwarfs, diversity that complicates generalizations about habitability. Standard interpretation treats the radio signal episode as a false alarm successfully identified and corrected. The planet detection, by contrast, represents solid science, confirmed through multiple independent analyses. An alternative hypothesis notes that the search for technosignatures, evidence of alien technology, has monitored nearby stars for decades without confirmed detection. The consistently negative results might indicate that intelligence is rare, that technology does not produce detectable signatures, or that searches are not looking in the right ways. The Ross 128 episode, where unusual signals were quickly explained conventionally, illustrates how the interpretation process operates. Whether this process might occasionally misclassify genuine anomalies remains an open question. The ship's trajectory arcs toward the next target. Sirius lies 8.6 light-years from Earth, the brightest star in Earth's night sky, visible across both hemispheres. Unlike the red dwarfs examined so far, Sirius A is a main sequence star significantly larger and hotter than the Sun. We approach Sirius, and the display immediately shows the primary star's brilliance, white hot at 9,940 Kelvin. But the sensors also detect a faint companion, Sirius B, a white dwarf, roughly the mass of the Sun, compressed into an object the size of Earth. This remnant completed its evolution from main sequence star to red giant to white dwarf long before human civilization existed. The core anomaly at Sirius involves historical records rather than current observations. Ancient sources, including Ptolemy in the 2nd century, describe Sirius as red, not white, not blue-white, red. This description contradicts the star's current appearance and any known stellar evolution pathway. No process could have changed Sirius from red to white in 2,000 years. Various explanations have been proposed. Ancient color terminology might have differed from modern usage, with red indicating brightness rather than hue. Atmospheric effects, when Sirius was observed near the horizon, might have reddened its appearance. The historical records might simply be errors, introduced during centuries of copying and transmission. None of these explanations has achieved universal acceptance. The red Sirius problem persists as a minor but genuine puzzle in stellar astronomy. Standard interpretation leans toward some combination of observational error and terminological confusion. The physics of stellar evolution strongly constrains what color Sirius could have displayed in historical times, and that physics does not permit a recent red phase. An alternative hypothesis, largely rejected by mainstream astronomy, proposes that Sirius B was still a red giant within historical times, contributing visible red light to the system. This would require stellar evolution to proceed much faster than models predict, a possibility considered extremely unlikely. Yet the persistence of the puzzle after centuries of discussion illustrates that even well-studied nearby stars can harbor unexplained features. The instruments record Sirius B's properties: surface temperature, cooling rate, spectral characteristics. White dwarfs cool predictably over time, and their temperatures provide age estimates for the systems they inhabit. Sirius B's temperature places the system at roughly 200 to 300 million years since the white dwarf formed, consistent with standard evolution models. The survey continues. Each stop adds data. Each star presents its own characteristics, and the pattern of small anomalies extends across the sample. Luton's star, a red dwarf 12.4 light-years away, hosts at least 2 confirmed planets, one within the habitable zone. The system demonstrates that planetary detection around nearby red dwarfs is possible when conditions favor it, contrasting with the ambiguous results at Alpha Centauri and Barnard's star. Epsilon Eridani, a Sun-like star 10.5 light-years distant, hosts a confirmed planet and a debris disk, suggesting ongoing planetary system evolution. The system is younger than the Sun, approximately 400 to 800 million years old, providing a glimpse of what our solar system might have looked like in its youth. Tau Ceti, another Sun-like star at 11.9 light-years, has been the subject of multiple planet claims, most unconfirmed. Like Alpha Centauri, it represents a case where detection efforts have produced ambiguous results despite decades of observation. Each star visited adds to the catalog. Each presents variations on the themes already encountered. The diversity is striking. Red dwarfs dominate the nearby sample numerically, but they span a range of activity levels, rotation rates, and planetary architectures. Sun-like stars appear more uniform in their properties, but still exhibit individual peculiarities. The ship pauses at the midpoint of its survey. The accumulated data requires processing, patterns require analysis, and the instrumentation requires recalibration before continuing. One pattern that emerges involves age estimation for red dwarfs. Determining stellar ages is notoriously difficult, relying on indirect indicators like rotation rate, activity level, and chemical composition. For red dwarfs, the challenge is severe. These stars change imperceptibly over billions of years, making it nearly impossible to distinguish a 1 billion-year-old red dwarf from a 5 billion-year-old one using standard techniques. This uncertainty propagates through many analyses. Habitability assessments depend on knowing how long a planet has been exposed to its star's radiation. Population studies depend on age distributions. Activity-age relationships used to predict stellar behavior require accurate ages to calibrate. The fundamental difficulty of dating red dwarfs introduces systematic uncertainty into all these applications. Standard approaches acknowledge this limitation and attempt to work around it through statistical methods or by focusing on stars with additional age constraints. But the limitation persists. An alternative hypothesis asks whether age estimates for nearby red dwarfs might be systematically wrong. If the relationships used to infer ages contain unrecognized biases, the entire nearby red dwarf sample might be older or younger than currently believed. This would affect habitability calculations, activity predictions, and population models across the board. Another pattern involves the census of faint objects in the solar neighborhood. Brown dwarfs, too massive to be planets but too small for hydrogen fusion, populate the nearby volume at rates that surveys continue to refine. WISE 0855-0714, discovered in 2014 at 7.2 light-years, has a temperature below Watta's freezing point, demonstrating that extremely cold objects can be detected if they are close enough. But the question of how many similar objects remain undiscovered is difficult to answer. Rogue planets, planetary mass objects drifting through space without host stars, represent another potentially undercounted population. These objects form either in circumstellar disks before being ejected, or directly from collapsing gas clouds at very low masses. Estimates of their abundance vary widely, with some models suggesting several rogue planets for every star in the galaxy. If these estimates are accurate, the solar neighborhood contains numerous unseen worlds that contribute to the local mass budget and gravitational dynamics. White dwarfs present similar census questions. These stellar remnants cool over billions of years, becoming progressively fainter. The oldest, coldest white dwarfs might have faded below detection thresholds, contributing to a hidden population of stellar remnants that current surveys do not capture. The common thread is incompleteness. The census of nearby objects, despite being the most thoroughly studied stellar sample in existence, might still be missing significant populations. The implications for understanding the local gravitational environment, for calculating encounter rates with passing objects, for assessing what might be out there unseen, all depend on how complete the census actually is. The ship resumes its survey. The remaining targets lie at the outer edge of the nearby sample, stars 15 to 20 light-years from Earth that still qualify as close neighbors in cosmic terms. Gliese 876, a red dwarf 15 light-years away, hosts a confirmed system of 4 planets, including 2 gas giants in orbital resonance. The system's architecture differs dramatically from our own, with massive planets orbiting far closer to their star than Jupiter orbits the Sun. Gliese 876 demonstrates that planetary systems come in configurations quite unlike the familiar arrangement of our solar neighborhood. 82, Eridani, a Sun-like star 20 light-years distant, shows evidence of 3 or more planets based on radial velocity measurements. The system represents another example of successful planetary detection around a nearby star, contrasting with the null or ambiguous results at some closer targets. The diversity of outcomes across similar stars raises its own questions. Why do some nearby stars yield clear planetary detections while others resist them? The answer might involve genuinely different planetary architectures, or it might involve factors affecting detectability that vary from system to system. Distinguishing these possibilities requires more data than current observations provide. The final stop on the survey is a region rather than a specific star. The outer boundary of the local bubble lies approximately 300 light-years from the Sun in most directions, though the bubble's shape is irregular. Our position near the bubble's edge places us within its hot, tenuous plasma environment, but close to the transition into denser interstellar medium beyond. The local bubble's origin in supernova explosions is well established. What remains less certain is whether the bubble affects anything beyond the interstellar medium itself. The hypothesis that bubble environment might influence stellar properties represents one of the more speculative ideas examined during the survey. No direct evidence supports it. The correlation between elevated flare activity and bubble residence might be entirely coincidental, an artifact of small sample size and observational bias. But the hypothesis remains technically testable. As surveys extend to stars beyond the bubble, as instrumentation improves, the question of whether bubble environment affects stellar activity can be addressed through comparison. If stars outside the bubble show the same activity distributions as stars inside, the environmental hypothesis fails. If they show systematically different behavior, the hypothesis gains support. The ship holds position at the survey's conclusion. All targets have been visited, all data collected. The return trajectory to Earth will take considerable time that can be used to analyze what has been gathered. The survey results can be summarized concisely. Among the nearest stellar systems, every one examined displays some feature not fully explained by standard models. Proxima Centauri flares beyond what its rotation should permit. Alpha Centauri hides its planets, if they exist. Barnard's star produces ambiguous signals that persist across decades. Wolf 359 belongs to a flare star population that appears locally concentrated. Sirius carries an unresolved historical puzzle. Ross 128 illustrates how unconventional signals are interpreted and potentially dismissed. Red dwarf ages throughout the sample resist accurate determination. The census of faint objects remains incomplete. Each anomaly admits conventional explanations. Proxima's activity might reflect poorly understood convective dynamo physics. Alpha Centauri's planets might simply fall below detection thresholds. Barnard's star signals might arise from stellar surface effects. The flare star concentration might be observational bias. Red Sirius might be ancient observational error. Age uncertainties might be irreducible, given red dwarf physics. Census incompleteness might be inevitable, given detection limits. But the accumulation of anomalies across the entire nearby sample suggests something worth investigating further. Either our models contain systematic errors that become apparent only when stars are studied in extraordinary detail, or the local stellar environment is genuinely unusual in ways not yet understood. The lithium abundance variations observed among nearby sun-like stars point toward the first possibility. Standard models predict more lithium retention than is actually observed in the sun, and nearby stars show a scatter in lithium abundances that does not correlate cleanly with age or other properties. The lithium problem indicates that stellar interior physics remains incompletely understood, that mixing processes operate differently than models assume. The local bubble hypothesis points toward the second possibility. If environmental factors can influence stellar properties, stars within the bubble might systematically differ from stars elsewhere. The hypothesis lacks direct evidence but offers a framework for interpreting several observed patterns simultaneously. Both possibilities carry implications beyond the nearby stellar sample. If models contain systematic errors, conclusions drawn from stellar observations throughout the galaxy might require revision. If local environment affects stellar properties, the solar neighborhood might not represent a fair sample of galactic diversity. The ship begins its return trajectory. The stars shift slowly as the course adjusts, the familiar configurations of the solar neighborhood giving way to the view from beyond. One question remains open as the survey concludes. The anomalies documented during this expedition are small, subtle, the kind that might be overlooked in less thoroughly studied samples. They do not overturn standard physics. They do not demand revolutionary explanations. They simply indicate that the nearest stars have not yet revealed all their characteristics, that features remain unexplained, that our understanding is incomplete. Whether these anomalies will resolve into conventional physics through improved models and better data, or whether they will eventually point towards something genuinely new, cannot be determined from current evidence. The investigation continues, patient and systematic, accumulating observations that future analyses will interpret. The stars closest to Earth have been watched for centuries. They will continue to be watched, measured, analyzed, questioned. Each generation of instruments reveals details invisible to predecessors. Each generation of researchers brings perspectives unavailable before. The process has no obvious endpoint. The nearest stars will keep providing data, and the data will keep raising questions. and the questions will keep driving investigation. The ship crosses back into the solar system. Earth appears in the forward display, a blue point growing slowly larger. The survey is complete. The analysis begins. But before the data can be fully processed, a secondary mission presents itself. The survey covered the most prominent targets in the solar neighborhood, but significant gaps remain. Additional systems warrant investigation, systems that might clarify the patterns observed or reveal new anomalies requiring explanation. The ship adjusts course. The next phase of the expedition will extend the survey to targets previously considered lower priority. Locale 9352 appears in the sensor range after a transit of moderate duration. This red dwarf lies 10.7 light-years from Earth, close enough to warrant detailed examination, but often overlooked in favor of more prominent neighbors. The star's properties are typical for its class: low mass, low luminosity, fully convective interior. The core observation here involves planet detection. Despite its proximity, Locale 9352 has been the subject of relatively few dedicated planet searches compared to stars like Alpha Centauri or Barnard star. Recent radial velocity monitoring has suggested the possible presence of planetary companions, but the data remains preliminary, insufficient for confident detection or rejection. Standard interpretation treats this as a resource allocation issue. Observing time is limited, and targets with higher profiles receive more attention. Locale 9352 simply has not accumulated enough data for definitive conclusions. An alternative hypothesis asks whether the relative neglect of middle-tier targets might be systematically distorting our picture of the nearby planetary population. If only the most prominent systems receive intensive study, and those systems happen to be unusual in some respect, conclusions drawn from them might not generalize. A more uniform distribution of observing effort across all nearby stars might reveal different patterns than currently apparent. The instruments rigid Locale 9352's baseline properties and whatever planetary signals might be present in the data. Whether these observations will prove sufficient for detection depends on factors that cannot be determined until the analysis is complete. The ship moves on. Groombridge 34, a binary red dwarf system, 11.6 light-years away, occupies the next observation window. Both components are flare stars, adding to the population of active red dwarfs in the solar neighborhood. The system has been monitored for planetary companions, with results similar to other nearby red dwarfs. Tentative indications that resist confirmation. The pattern of ambiguous planet detections around nearby red dwarfs is striking in its consistency. Proxima Centauri has one confirmed planet, but the system's architecture remains uncertain. Barnard star has a candidate planet that might or might not be real. Alpha Centauri has produced multiple candidate detections that failed confirmation. Locale 9352, Groombridge 34, and numerous other nearby red dwarfs hover in similar states of uncertainty. Only a handful of systems, like Ross 128 and Luyten star, have yielded detections robust enough to inspire confidence. The standard explanation involves detection limits. Red dwarf planets tend to be small, their host stars tend to be faint, and the signals produced are often at the edge of what current instruments can reliably extract. As instruments improve, more detections should become possible. But a detail complicates this picture. Detection sensitivity has improved steadily over the past 2 decades, yet the fraction of nearby red dwarfs with confirmed planets has not increased proportionally. Some systems that seemed promising initially have failed to yield robust detections despite intensive follow-up. The possibility exists that many nearby red dwarfs genuinely lack the kinds of planets we are searching for, that planetary formation or retention around these stars is less common than around sun-like stars. This possibility has significant implications. Red dwarfs constitute roughly 70% of all stars in the galaxy. If they rarely host detectable planets, the total inventory of potentially habitable worlds might be much smaller than optimistic estimates suggest. The sensors complete their observation of Groombridge 34. The binary components show their characteristic activity, flares detected during the observation window, adding to the baseline data. The ship rotates toward the next target. DX Cancri lies 11.8 light-years from Earth, another red dwarf in the crowded local census. This star has received attention primarily for its flare activity, which is particularly intense even by red dwarf standards. The flare frequency and energy output exceed most comparable stars, making DX Cancri one of the most active objects in the immediate solar neighborhood. The observation at DX Cancri focuses on flare characteristics, duration, energy, spectral distribution, recurrence pattern. Each flare event provides data about the magnetic processes driving stellar activity, data that can be compared against theoretical predictions and against observations of other flare stars. The comparison reveals both similarities and differences. Flare mechanisms appear consistent across active red dwarfs. Magnetic reconnection events, releasing stored energy in sudden bursts. But the intensity and frequency vary widely between stars of similar type, indicating that factors beyond basic stellar parameters influence activity levels. Rotation rate is one factor, but as Proxima Centauri demonstrates, the rotation-activity relationship is not straightforward. Age might be another factor, but red dwarf ages are difficult to determine. Magnetic field topology, convection patterns, and other internal properties might play roles that are not yet well characterized. The ship continues through the extended survey. Each target adds to the database. Each presents its own variations on the themes already established. Captain's Star, a red dwarf 12.8 light-years away, is notable for its extreme velocity through the galaxy. This star moves faster relative to the Sun than almost any other nearby object, suggesting an origin in a different galactic population, possibly even in a dwarf galaxy that was absorbed by the Milky Way billions of years ago. 2 planet candidates have been proposed, both disputed, with recent analyses favoring stellar activity as the source of the observed signals rather than genuine planetary companions. The Captain's Star episode illustrates how stellar activity complicates planet detection. Activity-induced signals can mimic planetary signatures across a range of periods and amplitudes. Distinguishing real planets from activity artifacts requires careful modeling of stellar surface effects. Modeling that depends on understanding magnetic processes that remain incompletely characterized. The ambiguity at Captain's Star is another instance of the pattern seen throughout the nearby red dwarf sample. Teegarden's Star, a particularly faint red dwarf, 12.5 light-years from Earth, was discovered only in 2003 despite its proximity. The star's extreme faintness, among the lowest luminosities known, kept it hidden from earlier surveys. Teegarden's Star hosts 2 confirmed planets, both potentially within the habitable zone, making it one of the more promising nearby systems for habitability studies. The late discovery of Teegarden's star raises census questions. If a star this close to Earth escaped detection until 2003, what else might remain undiscovered? The surveys that found Teegarden's star have continued to operate, revealing additional faint objects, but the completeness of the nearby census remains uncertain. Brown dwarfs fainter than current detection limits, rogue planets too cold to emit detectable radiation, ancient white dwarfs that have cooled below survey thresholds, all might contribute to a hidden population that affects mass estimates and dynamical models for the solar neighborhood. The ship pauses to recalibrate instruments after the extended observation sequence. The stellar targets examined during this phase have reinforced the patterns observed earlier. Widespread activity among red dwarfs, ambiguous planetary detections, census uncertainties, and systematic challenges in determining stellar properties like age. The next phase of the survey addresses a different category of objects. Brown dwarfs, the substellar objects intermediate between planets and stars, populate the solar neighborhood in numbers that surveys continue to refine. Lumen 16 appears in the sensor range as the ship approaches. This binary brown dwarf system lies just 6.5 light-years from Earth, making it the closest known brown dwarf system and the third closest system overall after Alpha Centauri and Barnard's star. Both components are warm enough to emit detectable infrared radiation, allowing detailed characterization of their atmospheric properties. Brown dwarf atmospheres are unlike stellar atmospheres. They contain clouds of exotic compounds, silicates, iron droplets, sulfides. Weather patterns develop as these clouds form and dissipate. The two components of Lumen 16 differ in their cloud coverage despite similar temperatures, demonstrating that atmospheric dynamics can vary significantly between otherwise similar objects. The core observation at Lumen 16 involves variability. Both components show brightness fluctuations as their atmospheres rotate, revealing the distribution of cloud coverage across their surfaces. These variations provide information about atmospheric circulation that cannot be obtained through any other method. Standard interpretation treats brown dwarf atmospheres as analogous to giant planet atmospheres, governed by similar physics but at higher temperatures. The observations at Lumen 16 generally support this framework, with cloud formation and weather patterns following predictions from atmospheric models. An alternative hypothesis proposes that brown dwarf atmospheres might exhibit phenomena not seen in giant planet atmospheres, driven by differences in internal heat sources, rotation rates, or magnetic field effects. Some variability patterns observed in brown dwarfs do not match model predictions precisely, suggesting that current atmospheric models might be incomplete. The ship continues toward the coldest object yet visited on this survey. WISE 0855-0714 lies 7.2 light-years from Earth, the coldest brown dwarf known, with a temperature between 225 and 260 Kelvin, below the freezing point of water. This object is so faint that it barely registers in the optical sensors, detectable primarily through its thermal emission at infrared wavelengths. WISE 0855-0714 demonstrates that extremely cold objects can exist in the solar neighborhood, objects that might have escaped detection entirely if they were only slightly more distant or positioned unfavorably for observation. The discovery of this object in 2014 prompted surveys to search for similar cold brown dwarfs, but the yield has been limited. Either such objects are rare or they remain below current detection thresholds, even at close distances. The boundary between brown dwarfs and rogue planets is not sharp. Objects below approximately 13 Jupiter masses cannot fuse deuterium in their cores and are typically classified as planets if they orbit a star. But the same mass object, drifting freely through space, occupies an ambiguous category. The classification matters less than the physics. Objects in this mass range share similar internal structures and atmospheric properties regardless of their formation pathway or current orbital status. The question of how many such objects populate the solar neighborhood remains genuinely open. Estimates vary by orders of magnitude, depending on assumed formation rates, ejection frequencies, and detection efficiencies. The conservative estimate places roughly one free-floating planetary mass object per star in the galaxy. The liberal estimate suggests several per star. Either way, the population is significant, potentially exceeding the number of stars themselves. If the liberal estimates are accurate, the solar neighborhood contains numerous unseen worlds drifting through interstellar space. These objects would contribute to the local mass budget, affect gravitational dynamics, occasionally pass through the outer solar system. The implications for comet perturbation, Oort cloud stability, and long-term solar system evolution depend on population densities that remain poorly constrained. The ship completes its observation of WISE 0855-0714 and prepares for the return trajectory. The extended survey has covered additional stellar and substellar targets, adding data to the accumulating picture of the nearby cosmic environment. The composite findings can be assessed during the transit back to Earth. Red dwarfs dominate the nearby stellar population numerically, but they present consistent challenges for characterization. Activity levels vary in ways not fully predicted by rotation rate or age. Planetary detections are more difficult than around sun-like stars, with a large fraction of systems remaining ambiguous despite intensive observation. Age estimation is fundamentally limited by the slow evolution of these stars, introducing systematic uncertainty into all age-dependent analyses. Sun-like stars in the nearby sample are fewer but better characterized. Their activity levels, compositions, and ages can be determined with greater precision. Planetary detection is more straightforward when planets are present. Yet even these stars present puzzles. The lithium abundance variations among nearby solar analogs, the occasional compositional anomalies suggesting unusual formation conditions or galactic migration, the historical puzzle of red Sirius that remains unresolved. Brown dwarfs and potentially colder objects represent a population whose completeness is uncertain. The discovery of WISE 0855-714 and Teegarden's star demonstrates that objects can remain hidden at close distances, implying that the census is not complete. The population of free-floating planetary mass objects might be large, potentially exceeding stars in number, but current surveys cannot reliably constrain it. The local bubble environment remains a potential factor in all these observations. If bubble conditions affect stellar activity, planetary formation, or other properties, the nearby sample might not be representative of the galaxy as a whole. This hypothesis lacks direct evidence but provides a framework for understanding why nearby stars might show unusual characteristics. The alternative possibilities raised throughout the survey share a common feature. They suggest that the nearby stellar environment might be less well understood than standard assumptions imply. Each possibility might be wrong, The conventional explanations might be entirely correct, but the accumulation of anomalies across multiple categories of objects and multiple types of measurements suggests that something warrants closer examination. Future observations will address these questions through several approaches. Next-generation extremely large telescopes, currently under construction, will provide angular resolution and sensitivity exceeding current capabilities. These instruments will enable direct imaging of exoplanets around nearby stars, atmospheric characterization of potentially habitable worlds, and more precise measurements of stellar properties across the sample. Space-based observatories, including successors to the James Webb Space Telescope, will extend spectroscopic coverage and achieve sensitivity levels impossible from the ground. The detection of biosignatures in exoplanet atmospheres, if they exist, will become feasible for the most favorable nearby targets. Astrometric missions will refine proper motion and parallax measurements, improving distance estimates and enabling more sensitive searches for planetary mass companions through gravitational effects on stellar positions. Surveys for faint objects will continue, using infrared and microlensing techniques to detect brown dwarfs, rogue planets, and ancient white dwarfs that current methods miss. The census of the solar neighborhood will become more complete, though some population of undetected objects will likely always remain. Each new observation will test the hypotheses raised during this survey. The flare activity excess among nearby red dwarfs will either persist or dissolve as samples expand. The pattern of ambiguous planetary detections will either resolve into confirmed systems or confirmed absences. The census incompleteness will either be filled in or remain as a persistent source of uncertainty. The ship enters the final approach to Earth. The planet grows in the forward display, blue oceans and white clouds becoming distinguishable as distance decreases. The survey has covered approximately 30 stellar and substellar systems, accumulating data that will require months to fully analyze. The initial assessment is provisional. The nearest stars exhibit anomalies that standard models do not fully explain. The anomalies might reflect model limitations that better physics will resolve. They might reflect local environmental effects that distinguish the solar neighborhood from other regions. They might reflect fundamental aspects of stellar and planetary physics that apply universally, but become apparent only through detailed observation. No single explanation accounts for all the observed features. The flare activity excess, the planetary detection difficulties, the compositional variations, the census uncertainties. Each might have a different origin, or they might share a common cause not yet identified. The investigation continues through the data that has been gathered. The nearest stars have provided observations spanning every category of anomaly identified at the survey's outset. Whether those anomalies will resolve into understanding or deepen into further questions depends on analysis yet to be completed. The ship touches down. The expedition ends. The data remains.